Hi, this is the circuit for my FSM for my microprocessor. So for the first state, which is known as fetch one, my the contents of my program memory, which is what I will get into later, is loaded into my instruction registers. In the next state, fetch two, my program counter is incremented, and the instructions and my instructions are loaded to the bus. And stage three, which is execute one, what's loaded onto the bus is allowed to travel onto the bus and goes to the next destination. And in the final state, which is execute two, I enable the tri-state buffer E underscore ALU, and that allows everything the final instruction to be carried out for each instruction. So like because the tri-state buffer E underscore ALU allows everything from the ALU to go to register A, which is what our final destination for most of the instructions are. So now taking a look at the output, I have 10 different outputs that are determined by the instruction register in the current state. All of this is just a computational logic of each different output. This output increments the program counter. This output loads instructions into the instruction register. This this output is a tri-state buffer that loads content from the bus onto no loads content from the register onto the bus. This is a tri-state buffer that controls what's in register A and loads it onto the bus. This is another tri-state buffer that allows the contents of the ALU to be loaded into register A. This output right here is a tri-state buffer that allows the contents of register A to be loaded onto the bus. This output controls whether we can add or subtract the value. This output controls whether we can load content from register B into register A, and this output controls whether we can load contents from register A into the ALU, and this controls whether we can display the outputs of register A. So now for the instruction registers, a total of 8 bits are loaded into the instruction register. 4 of them go into the instruction register, and then 4 of them go into the data register. Enable for both of these registers are connected to load instruction. This makes sense because you want to load the output of the FSM into the instruction register so that we output the correct instruction register value, and then we correctly enable, hold on, if we go to main, this output over here for the instruction register is EIR, so we connect. So this is important too. This output is important because this controls what is loaded from the instruction register onto the bus. So that output is important to make sure that that is done right. So that is there, and then this gives us the correct instruction register, and then both of these are connected to a universal clock and a universal reset, which is what I will get into later. So program memory over here. So you have 16 constant values that the circuit is looking for. So at specific like values, it tells the circuit to do something. So when the first digit is a 5, we want to load the second digit, the value of the second digit, into register A. Whenever the first digit is a 2, we subtract this second digit from whatever is in register A, If the first digit is a 1 right here, we add the second digit into register A. Whenever we see a 4, we display whatever is in whatever is in register A out to register O, and then whenever we see a 3, we directly compute the value of the second digit into register A. And so the output for the program memory is a memory tunnel for instruction, and then a memory instruction for data. So if we take a look out of that, that was program memory. So here it is. So we input the address, which comes from our program counter, into the program memory, and then we get our instruction memory and our data memory. So that helps us figure out. So we implement them into instruction memory and data memory. So when those go, so when we output those go directly into directly into the instruction register, and that's what also helps us get a correct IR and EIR. And then my ALU over here is simply just a 4-bit adder. It basically adds by 2 complements. So whenever this is 0, this is actually putting in a 1, and we get the invert of B and add A and add and when it adds that all up together, it's basically subtracting. And then the opposite for addition. So whenever this is a 1, it's inputting a 0, and we get the regular of A and B that's added in the adder, and that outputs that out. So that was the ALU. And then finally, we have the bus, where it's the bus, which basically helps connect which carries all the data and components to each of their respective destinations and connects everything together. So yeah, we have that. So as you can see with all these different cells, some of them have common inputs and outputs. So we made those tunnels because they are supposed to be connected. And then for so I told you whenever you see C and R, those are referring to clock and reset respectively. So this is how we have a universal clock right here, and this is how we have a universal reset with this button. And then if we just enable the simulation and allow it to run, I mean, there are some errors, but for the most part, it is like still like running how it should be. So there.